This research paper introduces the concept of self-consistency, SC, in large language models, LLMs, and its application to program repair. The SC approach involves prompting the LLM to generate both an explanation and a solution, then repeatedly sampling the model with high temperature to produce varied perspectives on the problem. By choosing the most frequent answer from these perspectives, SC has shown significant improvements in various natural language tasks. The authors explore applying SC to program repair, utilizing commit log messages as the reason within the few-shots. They find evidence suggesting that SC improves performance on the code repair task, particularly when using correct commit log messages. The richness of the space for representing prompts in modern, instruction-tuned neural language models allows for a wide range of prompt construction, leading to different autoregressive generation possibilities. The paper highlights the potential of SC in enhancing the effectiveness of LLMs in solving complex problems in software engineering, particularly in program repair. It demonstrates how leveraging commit log messages as explanations can significantly enhance the quality of generated patches. Program repair involves retrieving buggy functions, commit messages, and fixed functions using few-shot learning, a technique that assembles a few input-output pairs into a prompt, allowing the model to complete the prompt without requiring weight updates. This approach has been applied to various software engineering tasks, including code summarization, code repair, assertion generation, code mutation, test oracle generation, and test case generation. In few-shot learning, selecting specific few-shot samples using an information retrieval-based approach, such as BM25, can improve performance. For instance, Figure 1c illustrates the input-output of the BM25-based few-shot learning method for program repair tasks. Chain of thought is another approach that forces the generation of intermediate reasoning steps, substantially improving large language model performance on complex reasoning tasks. Each shot in chain of thought consists of an ordered triplet of input, reasoning path, and output. A prompt includes several triplets, followed by a target input, and the model generates the reasoning path and output. However, creating reasoning paths for fuse hotting can be challenging, especially in software engineering datasets where reasoning paths are rare. The authors propose that a summary or commit log message could serve as a reasoning path, as illustrated in Figure 1d, where the model is prompted to generate the reason or commit message prior to generating the fixed function. Self-consistency-based generation is another approach that improves over the naive greedy decoding approach used in chain-of-thought prompting. Self-consistency starts with a prompt with few-shot chain-of-thought triples ending with a target input, prompting the generation of a reasoning path and an output. However, self-consistency posits higher temperature generation, sampling a collection of distinct reasoning paths and outputs, rather than greedily sampling a single reasoning path and output. This approach enables the model to generate more diverse and accurate program repairs. Researchers have explored the application of self-consistency and chain-of-thought prompting in program repair tasks, utilizing the code DaVinci 002 model with 175 billion parameters. The study focuses on the MODIT dataset, comprising bug fix commits and commit messages from GitHub, which serve as reasoning paths for self-consistency and chain-of-thought. The authors investigate three research questions: whether self-consistency improves program repair performance compared to the baseline method of Nasheed et al., how performance varies with the number of generated reasoning paths, and whether actual commit messages are useful as reasoning paths. The proposed approach involves comparing the performance of greedy decoding, chain of thought, and self-consistency in generating correct patches. Chain of thought uses triplet shots in the few-shot prompt to induce the model to follow up the target input with a reasoning path before generating the output. Self-consistency, configured with a temperature of 0.7, generates more diverse reasoning paths and outputs for the target input. In the experiment, up to 50 sequences are sampled for each of the 1,000 target test cases, with a focus on the first 30 samples for reporting results. The results, presented in Table I, show that self-consistency improves performance over the baseline method, particularly when combined with BM25. The use of self-consistency also leads to a higher relative gain over the greedy plus BM25 baseline. This study demonstrates the effectiveness of leveraging commit messages as reasoning paths in program repair tasks and highlights the potential for further improvement by optimizing the number of generated reasoning paths. The proposed approach, CO-T and SC, demonstrates superior performance in the program repair task when compared to a baseline using BM25 for selecting few shots. The study reveals that CO-T and SC significantly outperforms greedy decoding by 42.10% and 38.39% for the datasets B2Fs and B2FM, respectively. However, when employing BM25, the improvements are less pronounced at 9.65% and 13.08%. A McNamara test confirms the statistical significance of these enhancements. An examination of how the number of samples influences performance indicates that the first 10 samples are pivotal for both datasets. Furthermore, the use of original commit messages is crucial for achieving better performance, as utilizing random commit messages does not yield substantial improvement. This underscores the importance of leveraging meaningful contextual information in enhancing the accuracy of program repair. Please provide the transcript that needs to be refined, and I'll transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you've outlined. I'll maintain the technical accuracy and depth of the content, explain key terms and concepts with precision and clarity, and highlight novel ideas, significant findings, and important arguments presented in the original text.